So we start this lecture with Sarah. Do you have an H?
Yeah.
Is angry. And make everybody that watches this video wonder why. If you email me and you know the reason why, extra credit.
Oh.
Except this class that I'm teaching.
Oh,
All right, so let's do limits involving infinity, which you actually have done this before. They just didn't tell you that's what you were doing, meaning when you were looking. Such a dirty word, isn't it? Up your asymptote. All right, so if I have this 1 over x rational function and I graph this, you were told a long, long time ago that this thing, x-axis here, was the horizontal asymptote, which is true, okay? And they just defined it. Depends on your teacher how they defined it. Most of them would say as x is getting very, very large, what's the value of your function getting close to? It never touches it because you can't divide by 0. So the whole concept of this was already there. We're just going to say it in more of a calculus way, okay? Meaning as x approaches infinity, still as x is growing very, very large, what's the value of my function getting near? Remember, that's what a limit is. So if you want to do a proof with this, it's the same, you know. All this stuff here pretty much looks the same. The only difference is I say as x is heading to infinity, I could be heading towards an actual limit, 0. And I can pick a value, like if you're interested in some limit, let's call it m, I'm always going to be able to pick a value larger, right? Because x is heading to infinity. And so that's all this is saying. Of course, the same thing with minus infinity, but I would be able to pick a value smaller. So this is how what you would use to go through a formal proof. Now, so I want to show that the limit of 1 over x equals 0 as x heads to infinity. So what I would do is graph it, because I don't want you to get, you know, we get writing all this junk over here, and I don't want you to forget what you're doing, meaning that we're trying to see as we're approaching, as this is getting very large, what is the value of my function approaching? Well, logically, you can see, again, as this is getting large, it's approaching 0. Do it with the proof. This is my f of x minus my limit, okay, equals my epsilon. Well, notice that, of course, just goes away, and I can say, well, as long as, and I mentioned this before, as long as when you do a proof, you leave this in terms of epsilon, you're done, because I can pick any error that I want, and I can say I can always stay within this band here, okay? In other words, I can switch places here and say that I can always pick any value that will stay within this band of 1 over epsilon, and then, of course, there's a minus there. I always ask on tests, because sometimes some of y'all missed on that negative, the -6, if you don't notice that negative sign there. But the same thing for the negative. Of course, now I'm going more negative this way. I can stay within that band. Now, this again is one of these. There's the proof. There it is. Now, I just want you to, whoa, I've never seen that before. Let's go like, is that burnt orange or is that red? The eyes of Texas are, okay, I'm good now. Did it change? Oh, I'm awesome. I'm feeling good now. All right. So anyway, we're going to use these definitions. Okay. So they've been defined. We've proven it, shown it. Okay. But now I just want you to remember it. Now, how I remember stuff like this is kind of a logic thing. I say, okay, x is getting very, 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 very large. That's what infinity means, right? But this fraction is getting smaller, 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 smaller. It's going to 0. And that helps me remember, you know, because you know me, I'm not a memorizer. I like to think more logically of this. And again, draw. All right, you've seen this before. This was our Theorem 1 where we had the limit laws. Nothing looks different. All we're saying here is you could replace all of these c's with infinity or minus infinity, and these same laws hold. Meaning that if you have, and again, we haven't gotten into high enough level things yet that you probably have to separate these, but if we have something here like a trig function and a logarithm, if you have to separate them, you can find the limit of one, the limit of the other, and then just simply add the limits instead of trying to add the functions together. All right, so some examples. is, let's say, I guess you can see that color okay. I want to find the limit of 5 plus 1 over x as x goes to infinity. If you've been paying attention, what's the answer now? Thank you. So technically, it's got something going on now. Technically, how you're supposed to do this is break it apart and say the limit of 5 plus the limit of 1 over x. And again, this technically is just getting your understanding. It's not, do I have to show all that work? No. It's understanding that we know that this limit here, that's just the function y equals 5, just the line. Well, if you go out to the moon, you know, to very, very large x, your y value is still going to always be 5. And that's the one that I said we're going to use this definition. Okay, so remember that was just defined earlier. And then, of course, we get 5. I think I don't have another slide, so I think I'm going to have to squish this. All right, how about another example? The limit of 2 over x minus 3 as x goes to infinity equals what? -3. I heard a little pause, and that's probably good because you were looking at this, hopefully, and saying, well, I haven't told you what that limit is, but we have that law that says I can bring that 2 out front. And so basically I have that minus the limit as x goes to infinity of 3. 2 times that limit we have defined as 0, and then of course that's -3. Okay, again, this is just trying to be, you know, most mathematicians like to be very precise. I have not told you that definition, but we have said that I can bring this 2 out here, but you're going to get to the point you're just going to be able to look at something like that. If I had, for example, the limit of pi minus 2 over x squared as x goes to minus infinity, what's the answer? We like pi. I don't even think I can draw a pi. It's a pi. That's the steam. It's a pi.
A for effort.
Sarah, give me an A. All right, so again, if you're being all mathy, what you should do with this is not only bring the 2 out front, but we haven't even talked about 1 over x squared, but that's the same thing as multiplying 1 over x times 1 over x. And we have said the minus infinity, that was also on that same slide, proven. So this, of course, is pi, 2 times 0 times 0, and then, of course, I get pi. Okay, so again, these extra steps I'm doing right now are just so you can break these apart when these get even more complicated. But you're gonna get to the point where you're gonna see, again, logically, you know, who cares about this value if this is growing very, very fast. Once again, my fraction's getting very, very small. All right. And, I guess I had graphs of each one of these. Oops, I forgot. So each one of these that I just did, I went ahead and graphed them. If you're interested, because I realize everybody in the world does not have an iPad, I don't know why, and I got to tell y'all something that reminded me of something else. This is a graphing program that you can put on your laptop, you know, so if you're interested. I like this graphing program because, again, it's like on the iPad, you can zoom in, you can do lots of functions. I mean, it's very nice, and in fact, when we do area under curves, which is the last part of this course, it'll calculate the answer for you. So it's kind of nice about that. No, so I heard this morning that, you know why iPhone 6 sales were so high? Because everybody wants one right now. Because it was not released in China. So all these people came over here and bought them and took them back to China, and they're selling them for like 4,000 or 5,000.
Yeah,
And I thought, man, that's a good idea. So when you leave here, go get a bunch of iPhones and go to China and sell them, okay? Because I told you this, I'm only asking for 25%. All right.
First guy who got the idea.
Yeah, everybody, to me that was hilarious. But the box is kind of weird, you know, because it's almost vacuumed.
Like without a case, yeah,
it's going to come out.
Switch the test to the 29th and I'll give you 100%.
All right, so here was my graph of the -3. Again, because I don't want you losing sight of what we're doing. We're saying as x is getting very, very large, we're heading towards, again, you've known this already. This is an asymptote, but how you learned it probably, graph, there's pi. Another reason I like this program is you can even put your axis in with trig values, you know, like pi over 2, stuff like that. Just, I don't know, it's just a program that I used to use all the time in here until I started doing. All right, so again, here is your definition. A line y equals b is a horizontal asymptote of the graph of a function y equals f of x. If your x is heading, as it heads to infinity, is heading towards that value, or minus infinity, it's heading towards that value. Again, this is something hopefully you already knew and you remember, okay? You knew what a horizontal asymptote was, but again, for most of you, it was just what was the value the function was getting close to? Well, in this case, we're saying as it's growing large or very small, meaning. All right, so let's see if you remember some things with asymptotes. If I have 5x squared plus 8x minus 3 all over 3x squared plus 2, for those of you that remember right away, what's the horizontal asymptote? Remember the little trick? What is it? -3 over. You're thinking right. You're just go to the other side.
Oh, negative.
5/3. So when I looked at that and I said you're just on the wrong side. So when the degrees are the same, so the degree of the numerator equals the degree of the denominator, you simply take those coefficients, okay, and so your horizontal asymptote equals 5/3. That was a little, I don't want to say it was a trick, it was defined that way for you in algebra class. Well, now we're gonna actually prove that with limits, okay? So again, this stuff, and if you're doing this at home in my math lab, I went through, because I did some of my math lab problems I'm going to show here in a little bit. I went through my math lab, and if you know these little tricks, you can finish the problems that fast, you know. Now, of course, on Cindy's test, I'm going to want to see all this mess, meaning that if I want to find the limit of 5x squared plus 8x minus 3 all over 3x squared plus 2, as x heads to infinity. All that I just wrote is the definition of the horizontal asymptote. It's that limit. Well, how you do these is you're trying to get things in terms of that whole 1 over x thing, because that's the only thing I've defined for you today. So what I would do is I would divide and I just want to see how many of you would write it in your notes. I'm going to divide and conquer every term by x squared, which is the highest degree in the denominator. Denominator. So I'm going to take every single one of these. Shaboop. What the heck happened there? There's a ghost. And so I'm going to take each one of these and I'm going to say, okay, the limit as x goes to infinity, you don't get my way there, 5x squared over x squared plus 8x over x squared minus 3 over x squared all over 3x squared over x squared plus 2 over x squared. Okay, again, the reason why is my only definition I have is I need things over x's because they go away because of that limit. So if I rewrite this, this becomes the limit as x goes to infinity. Well, that just becomes 5. This becomes 8 over x minus 3 over x squared. That becomes 3. And that just stays 2 over x squared. We just showed by x, 1 over x times 1 over x, that becomes 0, that becomes 0, that becomes 0. Guess what? There's your answer. So it works the same way of that little trick you learned back in, I guess you learned this stuff in algebra. I don't think this is pre-cal. That you learned in algebra to be able to find this by picking those leading terms, but this is the reason why, is with the proofs with limits. And again, all of this is going based off on that definition that the limit of 1 over x as x heads to infinity is 0. So all of this was just based on that definition. So you'll see that's how you would work all of these problems, meaning the calculus way. Okay, that's how you actually do the proof. All right, so I'm okay to go to a... All right, let's look at, and let me mention, I'm not going to, good Lord, what are you people doing? I'm not going to do oblique asymptotes, okay, in here. Maybe some of you remember that, yes. But if you're interested, they are in the textbook, okay? So I'm just going to bypass that. We're going to do horizontal and vertical only. Oh, So, I'm sorry, it's a bad day. Sarah didn't get her test today, and no oblique, such a nice word. Find the ha of 11x plus 2 over 2x cubed minus 1 from what you learned in algebra. What's the answer? 0, yeah. So this was a rule that they remember, is when the degree of the numerator is less than the degree of the denominator, then y equals 0, or the x-axis is the ha. So if you recognize stuff like that, again, you can get through your homework very quickly. However, you want to go through some examples like this, again, for testing purposes, meaning find the limit of 11x plus 2 over 2x cubed minus 1 as x approaches infinity. If you've been paying attention to the show, what am I going to divide every term by? X cubed, okay, because that's the largest in the denominator. So I take every one of these values, limit 11x over x cubed plus 2 over x cubed, 2x cubed over x cubed minus 1 over x cubed. And again, I can just look at this. Technically, we should do more steps and split things apart, but I know that's going to be a 2. I know you hate it when teachers do that. So that's going to be a 0, that's going to be a 0, that's going to be a 0, that's going to be a 2, right? But it doesn't matter because we end up with 0 plus 0 over 2 minus 0, which is 0. So what you might see on a test is I might even tell you what the horizontal asymptote is. Prove that the horizontal asymptote is equal to 0. And how would you prove it? You'd prove it by showing the limit. Okay, so that's how you do something like this. And so next, ladies and gents, now we say if we have a function that approaches infinity as we're heading towards a particular x value. So if you think about this, if you're interested in an x value and your function's heading towards infinity or minus infinity, this is your vertical asymptotes. Okay, all that other was horizontal, here's vertical. The definition to prove this, and we're not going to do one today, I'll probably do one on Friday, to actually prove one of these, is notice my interval, and this is going to make way more sense on the next slide, the picture. My interval stays the same, but I'm saying no matter some real number that you pick, my function's always going to be higher because it's going to infinity. Same thing down here is minus infinity, so it's always, again, I think the picture's more helpful. You still have your interval here you're interested in. That didn't change. That's centered around your x naught. We're just saying now any value you pick here to want to be your limit, that I can always pick something higher, always, no matter what you pick, meaning that this is heading to infinity or heading straight down to infinity. Again, you did this already. We just call them vertical asymptotes. Okay, so it's kind of nice. The theory is already in your heads that you did this stuff. It's just now with the calculus way. So a line x equals a, we have a vertical asymptote of the graph if y of a particular function. If I'm heading, and notice this is saying from the right side, if I'm heading towards a plus or minus infinity, this example here, of course, I'm heading to infinity. If I'm heading from the left side, it could also be going to infinity. We'll have an example of that, or in this case, heading down to minus infinity. And I know you say, woohoo, that's it. That's not it. I'm full of bad news today, ain't I? 1, 2, 1, 4. What did we just do? Infinite. Infinite. You'll be old and forgetful like me one day.